and separate it again. So this is 100. Now I'm gonna write this 4/5 to the first times 4/5 to the k minus 1. So I'm being clever here. I'm trying to rewrite this so I can get the n minus 1, or in this case k minus 1. I'm trying to get that in my formula, right? So I write the k wherever, well, I erased it. I tried to write that k as k minus 1 plus 1. And then I'm splitting it. This really is like 4/5 to the k minus 1 times 4/5 to the 1, but then I flip the order. Now, why do you think I flipped the order of these? Because in here it's to the back, right? So now, do I have a new constant though? Is my constant changed? Absolutely, it's changed. Look, it was 100, but now it's 100 times 4/5, which is really 80. So this is 80. If all this like weird manipulation that I'm doing is troubling you, well, this is the nature of the beast. This is the way it's going to be. All right? There it is. Does that look like this now? Yep. Okay, can you tell me that? So we right now can say for sure this is geometric, right? This is now a geometric series, for sure. And because it's geometric, all I have to do is identify what A is and what R is. Can you tell me what A is? 80. Can you tell me what R is? 4/5. Now, what is the test that we do according to your sheet when you have a geometric series? Check the absolute value of R. Okay? Now, in our case, the absolute value of R is the absolute value of 4/5, which is definitely less than 1, right? And if the absolute value of R is less than 1, then this thing does what? It converges. Not only does it converge, we know what it converges to, right? So therefore, continuing, therefore, have I used the 3 dots in here for therefore? If I haven't, I'm going to start putting 3 dots like that every time I want to write the word therefore. Okay, it's just shorthand. Therefore, this series, okay, converges to what? What is that thing headed to? I'm going to put equals. What is it headed to, according to the formula on your sheet? A over 1 minus R, right? Doesn't it say that? That this thing sums up to be A over 1 minus R. So what's A? 80 over 1 minus 4/5. So look on your formula sheet. A over 1 minus R. That was the formula we came up with on our own. Now this is the same as 80 over... What's 1 minus 4/5? 1/5. And then that's equal to, flip over, 400, right? 400. So think about this. What we're saying is that if you were to take 1 and plug it in here, you would get a number, right? Then you say plus, then you plug 2 into this, and you get a number. Then 3, then 4, then 5, then 6. And you do that, and what's going to happen is this thing is going to add, it's going to get closer and closer and closer to what number? 400. You're never going to go over 400, though. It's going to converge to 400. That's your first look at a geometric series, okay? Do you like it? Yes.
Did you say those 3 points meant?
Therefore, this word is now these 3 dots. Let's try another one. Sum. This was not a partial sum? No, that's the infinite sum. Okay, so look. When it comes to series, There are really only two types of series that we can actually find the sum of. Like we just said that this sum was 400, right? Geometric series and telescopic series are the only ones that we can actually find the numerical answer for. All the other series we do in here, we're just going to be able to say it converges or diverges. That's all we're going to be able to say. All right? All right, here, this one. Let's switch to n again, because I want to be able to interchange these. Let's go 5 to the n minus 3 times 7 to the 5 minus n. Ooh, this one will be interesting. So the first thing you would do is maybe an nth term test, right? Right? Nth term.
So you said that 400 that's the convergence number?
That is the number it converges to. Do you remember I had the picture a second ago that had all the dots? I had the dots that were coming down and then the dots that were going up. With the one we just did, our dots over here would be converging to 0 because we showed that. But then the series, the sum, would be heading up and there would be a flat line at 400 and we'd be heading towards 400 and we wouldn't go past it. That's what's happening for this geometric series. Now, looking at this one, the nth term test is there for us, right? We could run the nth term test. It would be kind of messy. But when we look at this, I want us to start to recognize that this is geometric. All right? The way you know something is geometric is because you have a base that's a number and your exponent contains the index in it, right? So this is like r to the n, right? You always have like your n up there. Now n minus 1. But these both have exponents with n in them, right? So I'm going to actually jump past the nth term test and I'm just going to go straight to trying to make this look like a geometric. So what do you think I'm going to have to do to make this look geometric? Start splitting them up, right? Start breaking things apart. So how can I rewrite that? How can I rewrite that 5 to the n minus 3? 5 to the n times 5 to the negative 3, right? Times 7 to the 5th times 7 to the negative n. Now, the thing I'm most interested in are the things that have n on them. Those are the things I'm most interested in. So is there a way that I could somehow combine this and this together? Because do y'all realize that these two right here are just numbers, right? These are just numbers. So I really don't care too much about those right now. All I care about is, can I get this and this together somehow so that that can be my r to the n minus 1, but I'll get to that later. Yeah? Okay, so let's try it. Well, isn't 5 to the negative, 7, that's not 5. 7 to the negative n, isn't that the same as like the 7 on the bottom with the n? So can I rewrite this as sum n equals 1 to infinity, what, 5 over 7, but both to the n? Right, I have 5 to the n, I drop this one down, 7 to the n, but then put them together, both to the n with division. And then everything else, well, those are big numbers, aren't they? 7 to the 5th over 5 cubed. I'm just going to leave those alone, right? No one wants to raise 7 to the 5th power. We could cube 5, but who cares, right? I dropped it down to the bottom. So this is looking right now like this is our a, and this is our r to the n, but it's not n minus 1. So again, we have to play that little game, minus 1 plus 1. Sum n equals 1 to infinity. I'll do it 5. Then it's going to be n minus 1, right? And then what's going to appear next to that? Just 5 over 7. So I'm not quite showing that step where I do minus 1 plus 1. I'm realizing that 5 over 7 to the n is really 5 over 7 to the n minus 1 times 5 over 7. Right? Put those back together, and you get back that. Is that too big of a jump? All right with that? Now I'm still missing 7 to the 5th over 5 to the 3rd, right? All of this is my A, right? That's all, whatever number that is, that's A. And then what about our R? This is our R. And is the absolute value of that less than 1? Yes. So does this converge? Yes. What does it converge to? That over 1 minus that. Okay. Let's do that. So this is geometric. A is equal to, I didn't bring my calculator. Do we want to really know what that is? Well, here, check this out. It's not as bad. This is 5, and that 5 becomes a squared, and then that 7, and that 7 becomes a fourth. So that's a little bit better. 7 to the 4th, right? Divide it. Yeah, I'm just going to do that. 7 to the 4th, which is 2,401 over, is that just 5 squared? Yeah, 25. Okay, so do y'all see that's my A? 7 to the 4th, 5 squared, that's it. And my R here is 5/7. And the absolute value of that is less than 1, so converges. So what if this was 7 over 5 instead? You would just say it diverges and you'd be done, okay? If these were flipped over, that number would be bigger than 1 when you take the absolute value, and then you just say diverge and there's nothing else to do. But for us, it converges, and because it's a geometric series, we have to actually put what it converges to. So what would this converge to? So this sum right here converges to, or you can put an arrow or equals, it doesn't matter, 2401 over 5, that's A, 25, over 1 minus 5 over 7. That's A over 1 minus R. And that is 2401 over 25 over, let's just subtract, this is like 7 over 7. So 2/7. And a fraction over a fraction, you flip, right? You reciprocate that. And what do you get? When you divide that, right, this is going to come up and be a 2 down here and a 7 up there, like that. I'll just do it on my calculator. Times 7. So I'm getting 16,807 divided by 50. Yeah, I'm just going to leave it like that. Who cares? I'm not even going to reduce the fraction. It reduces, like 2 goes into both of those, but that's it. That's the answer. That's what it converges to. What do y'all think? No? Yes?
Because I missed it. When you had 5 over 7
Uh-huh.
to the end, how did you make the jump from 5 over 7 n minus 1?
Okay, so I had 5 over 7 to the n, but in the formula I need a minus 1.
Right.
So I went minus 1 plus 1, but I didn't write that step.
Okay.
And then that splits into that. You got it? Okay, okay. All right, how about this one? Y'all ready for this? Okay. Have you ever, you've probably never noticed this before, but let's take, I want us to take I want to take this decimal. This decimal, 0.136.136.136. Now, what I'm about to do is you're going to be like, what? What does this have to do with geometric series? Okay? But just watch and enjoy. That decimal right there. I would like for us to convert it to a fraction. Seem reasonable? Like there should be something I could be able to type into my calculator that when I hit enter I get 0.136, 0.136, 0.136. What is it that I type in? Now your calculator, a lot of them have a button that can go from decimal to fraction. But will it do it, like is there a way to type this in forever on your calculator? I don't think you can. So you ready? Watch, check it out. Remember our positions here. Isn't this the tenths position? This is how many tenths we have. This is how many hundredths we have, right? The next one is thousands, and then 10,000, 100,000, yes? So this is the same as taking 1/10 plus 3 100ths plus 6 1,000ths, right? Plus 1 10,000th. You see what I'm doing here? I'm building up a decimal. If I put that and that together, I get the first two. I put all three together, I get the first three. And then if I continue that, that'll give me the whole thing, right? This pattern continues. Okay, but isn't 0.1 1/10? And isn't this 3 100ths? And isn't this 6 1,000ths? Right? And isn't this 1 10,000th? And what would the next one be? Let's just do a couple more. 3 100,000ths. Last one I'm going to do. 6 1,000,000ths. Right? Plus, and that keeps going, right? So those are the fractions I would have to type in. I keep doing that forever on my calculator, and I would get 0.1363636, right? All right. What could we do here? Is this not the same as 136 over 1,000? Let's see. Is that these three right here? If I asked you to put just those three together with a common denominator, is that what it would be? I would have to multiply the top and bottom of this by what to get 1,000? 100? Wait, hold on. I'm trying to get 1,000, right? So what would I multiply by? 100, right? So I'd multiply top by 100, bottom by 100. Here I'd multiply top and bottom by 10. With me? This one I wouldn't have to touch. So they would all have a denominator now of 1,000. And that way, when I put them together, it'd be 100 plus 30 plus 6. That's 136 over 1,000. Right? What would the next one be if I put these three together? 136 over the common denominator again, which this time would be 1,000,000, right? Do you have any guess as to what the next three would be? 136, good, over. How many more zeros do I need to add? 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Right? Can I keep going? I could keep going, right? But this is kind of going to get tedious. Now for the big part. This is the same as 136 over 10 cubed, right? Plus 136 over 10 to the 6th, plus 136 over 10 to the 9th, right? There's a pattern here. Plus 136 over 10 to the 12th, right? Dot, dot, dot. Okay. Now, is this not the same as, man, what are those things? These things are growing by 3 each time, aren't they? And I know how to generate a sequence that does that. Don't you know how to do that? Like if I asked, this will be on your test. If I said, hey, generate this sequence, could you generate that for me? What would the sequence be that generates those numbers? Don't worry, the test is only Tuesday. 3n. 3n would generate that, right? You plug in 1, you get 3. You plug in 2, you get 6. So I can actually generate these. So see if you agree with me on this. Isn't this just the sum as n equals 1 to infinity of 136 over 10 to the 3n? See, the 136 never changes, right? All that keeps happening is that your power below it keeps going up by 3. So if I plug in 1 to this, I get that one, right? Then plus, now I plug in 2 and I get that one. Plug in 3 and I get that one, right? That's almost geometric. It's almost geometric. I have to force it to be geometric, though. Watch me force it. It doesn't like me to do this to it, but I'm going to force it. That's the same. Right or no? The 136 is a constant, so I'm just going to pull it out front, right? I have 1 over 10 to the 3n, right? 1 over 10 to the 3n. I can rewrite that this way, right? Because the property of exponent says you could put that power here and here. What happens if I take 1 and raise it to anything? It's still 1, so that's 1 on top. And then the 3n on the bottom would give me 10 to the 3n. Do y'all see the r? It's geometric. Do you see a? Yeah. R? Crap, that's not what I wanted. I don't want 3n. What do I want? N minus 1. And so anytime I've needed something and it wasn't there, what have I done? I've just made it happen, right? Just made it happen. So here we go. I'm going to make it happen. 136, 1/10 cubed to the n. 1/10 cubed to the n. I'm going to start with that because I don't want 3n, I want n, don't I? But if I take something to a power, you're supposed to multiply those, and that would be 3n, yes? So this is really just this 136, and then 1/10 cubed is really 1/1000th. Right, that's what that is. But then to the n. But I don't want n, I want n minus 1 plus 1. Which means I'm going to have to pop a 1 over 1,000 off the end of this. When I pop the 1 over 1,000, I'm going to actually pop it out front. And then 1 over 1,000 to the n minus 1. So y'all understand what this is the third time I've done this. So y'all understand what I'm doing here? This right here is that one. Then the 1 on that is that one. And I can put those two together, right? Sum n equals 1 to infinity of 136 over 1,000. And then 1 over 1,000 to the n minus 1. And what? That converges, right? So A here is this, right? R is this. Is the absolute value of R less than 1? Yes, this is a convergent geometric series. What does it converge to? This converges to A over 1 minus, what's R? 1 over 1,000. Okay. What is 136 over 1,000 over, what's 1 minus 1/1000th? That's 999 over 1,000. And then flip, and when you flip, we get something really nice. 136 over 999. Now, get on your calculator and type in 136 divided by 999, and you're going to get 0.136, 136, 136, 136. Now, does this seem very useful? Probably not, right? But do you see how I turned a repeating decimal into a geometric series? Okay. There's a lot of stuff happening in here. So this this actually turns out is actually really pretty freaking awesome because this works for any repeating decimal. Watch. If I do this, you just give me a guess as to what you think this would be. 2, 4, 2, 4, 2, 4, repeating 2, 4, 2, 4, 2, 4. What do you think that is written as a fraction? 24 over 99. And you can check for yourself, that is. 24 over 99 is going to give you 0.24, 0.24, 0.24. Now, it would be a lot of work to show it with the geometric series, but that's what it turns out to be. There's something very crazy about this, though. Watch. So let me just try one more. What if we had 275, 275 repeated? That should be 275 over 999, which it is if you check it, all right? Here's something kind of blow your mind. Then what's 0.999 forever? Well, this repeats all the time, right? So I could just go back to this, right? And what we've been doing is we've been saying, okay, what does it repeat, right? So this is 24, and what we're doing is we're taking 24 and we're dividing by 1 less than 100, right? To get the 99. So it's like we're in the 100th position on the 4, so we use 100 down here and we subtract 1. Here we're on the 1,000th position on the 5, so we take the number divided by 1,000 minus 1. Does that make sense? So here we're in the 10th position, right? So if I take that number that's repeating 9 and divide it by the 10th position, 10 minus 1, I get what? Oh no, I get 1. Don't I? What does that mean? That means the number 0.999 forever is the number 1. That's what I'm here to tell you. This is the number. If you look at the number 0.999 forever, that is the same as the number 1. There is no number between these two numbers. They are the same number. It's impossible for you to find a number between the two. They are the same. That's do you like that? You don't like that, do you? I'll convince you another way, and this one might. Let me see if I can convince you. Let me call 0.99 forever. Let me call it x. All right, I'm going to try and convince you right now that x is 1. Okay, so what would 10x be? I'm going to put it above it. What would 10 times x be? So what happens whenever you multiply a number by 10? What happens to the decimal? It moves over to the right one. Are we all okay with that idea? Okay, so if I move that decimal over, this is 9.999 forever, yes? Okay, so now what if I ask you to subtract the 2? What's 10x minus x? Like algebraically, that's 9x, isn't it? Now what happens if you take that and subtract that? All this 0.99 crap at the end kills that off, right, when I subtract? And all you're left with is what? The 9 out front. Which means that x has to be 1. All right. Now I don't want to, I kind of simplified this whole repeating decimal thing. What if you had this? 0.121212. The wheels come off and the formula won't work anymore, okay? Just by putting that one little 0 in there. Or if I did something like this, 0.4121212. You see how that 4 is there now? That throws the entire thing off. It's only when you have something repeated from the beginning, 314, 314, 314, that you can then say, okay, that's 314 over, in this case, 999. Okay, that works like this, but it doesn't work for these. So I will offer this as a bonus. If you can turn that into a geometric series and show me the fraction that creates that. All right, you asking for bonuses? There you go, there's a bonus, all right? It's look, this is well within reach, and there are problems like this in the book. Like, I think there's an exercise set that has a few of these in it. So I'm not like throwing some random crazy thing at you, all right? Don't just go to Wolfram Alpha and type that in and then have it spit you out a fraction, because I need to see the geometric series, okay? All right. 2:30, man, we still have so much to do. Chapter 8 is just so dense. Let's talk harmonic and then we'll talk test, okay? At least let me introduce you to the harmonic. Harmonic's easy to talk about, I think. Harmonic series. Okay, here's what a harmonic series looks like. Sum n equals 1 to infinity of, do they have harmonic on your sheet here?
No.
They do not have harmonic on the sheet. Good. All right. C over n. So that's supposed to be a C. It kind of looks like a dying O. Let's see. C over n. Now here, C is a constant, all right? So let's look at an example of a harmonic, just so we can see what these look like. Specific example would be something like, well, 1 over n. Would that qualify? See, here C is 1, right? So what does this series look like? 1, 1, 1/2, right? 1/3. Keeps going forever? Yeah. Now, if I would have put a 4 here instead of 1, 4 over n, this would be 4, 4/2, 4/3. That would still be a geometric series. I'm sorry, I said geometric, harmonic. So what you're looking for with a harmonic is really that the denominator is linear. Do you see that that's a linear function of n? It's to the first power, n to the first power, and that the numerator is a constant. That's what makes it harmonic. All right, so I'll give you another example here. What about 10 over n plus 2? N equals 1 to infinity. Would that be harmonic? Yes, that is harmonic. So notice on any harmonic that if we try the nth term test, when we take that limit, that's going to go to 0, right? And that tells us nothing, right? That tells us nothing. So all harmonics are inconclusive when you run the nth term test. So what test do we use? And there is no test on here. And there's a reason why. And the reason why is because all harmonic series diverge. All harmonics diverge. I'm going to try and convince you why, all right? All harmonic series diverge. So can I try and convince you? Can I try? Okay, here we go. I'm going to try and convince you. And I'm going to try and convince you by taking the simplest one I can come up with, which is 1 over n. I'm going to use the whole width of this board to try and prove this to you. All right, here we go. This is 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth, plus a ninth, plus a 10th, plus an 11th, plus a 12th, 13, 14, almost there, 15, 16, okay, ... forever, right? Okay. All right, got it? Okay. I want you to notice something here. This is obviously 1, right? There's nothing crazy about that. And the next one is a half, yeah? Okay. I'd like for you to put these two together right now and tell me what that would be. The 1/3 and the 1/4, add them up. You get what? 7/12. Okay, plus. Now, I'd like for you to take the next 4 and add them up. All right, so we might need a calculator for this one, right? So who's got a fancy calculator that can give you the fancy answers? Like it'll leave it as a fraction and not go to decimal. Does yours do that? Try it. Do 1/5 plus 1/6 plus 1/7 plus 1/8. $533 over 840. Okay. All right. Now we can keep doing this, right? We can keep doing this, but now let's take the next 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's all of them, right? The next 8. Now, I don't want you to do that. Hold up. Time out. Time out. Don't do that. All right? But I want you to see something here. If I went back to this one, and instead of asking you to do 1/3 and 1/3, I did 1/4 and 1/4. And now I'm going to go back in front of this and put 1/2 here and in front of that 1. So I'm not going to touch this. I'm not going to touch this. But if I told you to do 1/4 and 1/4 instead of 1/3 and 1/3, 1/3 and 1/4, do you agree with me that these two numbers together are smaller than these two? Like what's a third plus a fourth is bigger than a fourth plus a fourth. Yes? But this is easier to add, isn't it? If I add those two together, what would I get? 1/2. Okay. Plus, now, instead of having you put all these together, what if I asked you to do 1/8 plus 1/8 plus 1/8 plus 1/8? Do you agree that this would be bigger than this? Yes? But these together are easier to add up. What would that be? 4/8? That would be another half, wouldn't it? Plus, now, if I did this, can you guess what I'm going to ask you to add here? 1/16 plus 1/16 plus 1/16? Right? If I added all those up, what would it add up to be? 8/16? That's going to be a half again, right? Okay. So do you see what's happening here with the blue one? The blue one is, what, this sum right here? That's the blue one, which is going to be 1 plus a half plus a half plus a half plus a half. What would that do if I kept doing that forever? It would go to infinity because you're just adding a number on top, one on top of the other, right? And they're not getting smaller. It's just a half on top of a half on top of a half. Wouldn't the blue sum diverge? Do you agree that this blue sum, when you add them up, would become infinite? Okay. And remember, you said that each one of these, this right here and this, you said that this was bigger than this, right? Yeah. And then you said that that was bigger than that. And that was bigger than that. That means this sum up here in purple would have to be bigger than or equal to this sum. And this sum's already infinite. So the only way that that can be bigger is if that's infinite also. Hope that makes sense. So all harmonic series diverge. All you ever have to do is recognize it's harmonic. You know, so you say, oh, fixed number over a linear function, done, harmonic divergence. All right? Talk about tests. You can't do the homework for this section yet, really. I mean, we still have to talk about telescopic. No, nothing I've said today is on the test, unless you want geometric series on the test. Y'all don't want J? Okay. Well, I didn't know if you would want them or not. Is that a solid, firm no from everyone for geometric series? Okay. Just 8. Yeah, so I put together a review, as you can see. So just do that, and you're good. Have a good weekend. This isn't really much of a review. It's stuff I've already said. But I actually sat down and typed it up. So I thought about it for at least 5 minutes. So the test is on Tuesday, right? The test is on Tuesday. The whole idea behind that is I want to get it graded before the drop date, which is Friday. Okay, so although we have, this is still a relatively healthy class. My Monday, Wednesday's down to 14. So, all right, so here's what I want. All right. Be able to set up the following types of integrals. Set up now. I know on your homework, that take-home problem set I gave you, I gave the same instructions of setting up, and a lot of you worked it all out, and I'm very happy for you and proud of you for doing that. I didn't reward you for that, I'm sorry, but all I wanted was the setup. You didn't have to do any simplification. On the exam, do not work them out. You're going to waste your time, and at the end, I'm going to be like, you ran out of time because you worked them out. Okay? Set them up only. All right? Area between two curves. So the things that I'd be concerned about here is you're going to have to find the intersections of the two curves. So you just got to be ready with your algebra to do whatever is necessary to figure out where they hit. On the take-home, if you did not show how you got to those intersection points, then I took off. And I know that cost some of you some points. That's because if you just looked at a calculator where it intersected and got the point, that's not showing me the work. All right, so please on the test be sure that you can do that algebraically, whatever it is, okay? Then solid, I'm going to give you a region between two functions and ask you to rotate it around the x-axis. X-axis, y is a constant, y-axis, and x is a constant. So just like on the take-home, the different lines, there were a few students who tortured themselves by avoiding shells on the take-home thing. Like, you know, I think it was numbers 5, 6, and 7 were all easily done but with shells. But some people went and took those equations I had up there and solved them for x, which wasn't that bad. But the only reason it worked was because it was easy to solve for x in that quadratic one. If you look on the thing, it was like y equals x squared minus 2x plus 1. If I would have made that y equals x squared minus 3x plus 1, then the right side wouldn't have factored as a perfect square, and then you wouldn't have been able to solve for x easily. So what am I saying? Use shells. It's so much easier to use shells. So much easier.
So we'll never have to use terms of y for the test?
I'm not saying that. I'm just saying that don't make it harder than it has to be. I'm afraid that people are like, well, I'm just not going to learn shells. I'm just going to solve for x. And that's what I'll do when I get to the test. The whole idea behind shells is that I can give you a problem that you can't solve for x. If I just give you y equals sine x, what are you going to give me, arc sine? I mean, like, you know what I'm saying? Like, just use the shells. It's easier. But you might have to solve for y. I mean, solve for x. You could. Not going to take it off the table because you had to do that in the homework. So, all right, so that's it. So all of that is like we've seen it, done it, right? Relatively speaking, yes? And then I give you some sequences. You find a formula. So I give you some sequences, and then I say, hey, you know, generate the formula for this. Even numbers, and then, you know, different powers, like we did in class. Then you have to find a limit of the sequences. So that was from the homework from 8.1. So this is all 8.1 right here. This is all 8.1. Give you a sequence, take the limit. Okay, if you need to use L'Hopital, make sure you tell me you're going to go to a function of x. And then you might have to use the squeeze theorem. Just anything from the homework assignment or what we did in class is fair game. And then the last one, I'm thinking this would be probably more like a bonus question. Where, not because I think it's harder or anything like that, but you just saw it like 2 days ago, and you know you need a little bit of time to mess with this. So I'm thinking as a bonus, I force you, I tell you, you must use the bounded monotonic sequence theorem to show that a sequence converges. So you have to go through all that, like you have to show it's bounded, you have to show it's increasing or decreasing, you have to convince me with your work that you know what you're doing, and yeah, that'd be a good bonus. So what do y'all think?
How many questions?
I don't know. I'm thinking by looking at this, I don't know. I can't see more than maybe 7 or 8, you know? Yeah. I'm not doing that on this one. Yeah. You might see it on the final. Yeah. This right here is what I want you to focus on. Yeah. 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 Now, that's not to say that I might not still send you home with something for that. Some things I want you to do in class under time constraints, and some things I might want you to do at home. All right, so I sent you all home with a pretty good problem set for solids of revolution stuff, but I haven't sent you home with anything on arc length or surface area, right? So that may still be down the road to come. All righty? Okay. Have a good weekend. I think I've given you a very narrow focus here.